What times y? Nope. What times y? Nope. 7. Those are our leading terms. B times b is b squared. I want to show you polynomial long division. Hello. We are looking at lesson 11-5. You can see I have that pulled up in front of me, and we are going to figure out how to divide polynomials. Now, what you might be wondering is, haven't we already done this, right? Wasn't the last lesson about dividing polynomials? And you'll notice, no, it wasn't. It was about dividing rational expressions. And so normally what we would do is we would say, well, what if you have x squared plus 6x minus 7 over x minus 1. And so we would say, oh, so we're going to factor this. That's going to be the same thing as x plus 7 times x minus 1 over x minus 1. And so after we factor, we just happen to notice, oh, we have some common factors that cancel out. And so that's why we can say this is the same as the expression x plus 7. Or maybe we take this same expression, x squared plus 6x minus 7 divided by x minus 1, and we say, let's actually take that whole expression and divide it by another rational expression. This one we will call x squared plus 7x over, say, 2x minus 3. Whatever. And so we would factor again, so that's still x plus 7 times x minus 1, still divided by x minus 1. But of course, the main thing we did yesterday is keep, switch, flip, right? So we divided by we took division by rational expressions and turned it into multiplication by reciprocals. And so this turns into times. The 2x minus 3 would go to the top. And then this right here, you should notice, oh, that's the same thing as x times x plus 7. And then from there, we might say, okay, so our x minus 1s cancel. Looks like an x plus 7 also cancels. And we end up with this expression at the end, 2x minus 3 divided by x. And all of that is stuff we did in the last 2 lessons, and it's also stuff that's still going to apply today. It's just that today we're going to be able to do an additional operation. We will actually divide 2x minus 3 by x. So that's why this lesson is called Dividing Polynomials. Before we get into example 1a, there's something I have to justify, because I've been really specific with you that, like, up here, 2x minus 3 over x. I've said over and over again, we can't do things like cancel the x and say, oh, so this is the same as 2 minus 3, which is negative 1. And again, you can see it's clearly not. If we have 2x minus 3 over x, and we say let x equal 10, for example, then that becomes 20 minus 3 over 10, which would be 17 over 10, or 1.7. But on the other hand, if we said let x equal 20, 2 times 20 is 40 minus 3 over 20 gives us 37 over 20, which would be the same thing as 1.85. And 1.7 and 1.85 are not the same, right? This expression changes its value depending on what x is, and definitely neither 1.7 nor 1.85 is negative 1. This expression, I don't even know if it can take on the value negative 1. Actually, as I think about it, the answer is yes, it can, but it's if x equals 1. If x equals 1, that does actually end up working out to be negative 1. But again, it would only be in that one specific circumstance. So we can't cancel like that. But there is something else we can do with this expression. So let's take our 2x minus 3 divided by x. And I'm not going to cancel the x, because I see that plus or minus sign, in this case a minus sign, and I know I'm not supposed to just cancel part ways when I see that plus or minus sign. But it's that part ways that's the important part. I can cancel if I'm careful about it, and if I make sure to cancel x out of everything. What does that mean? Let's replace the word cancel with divide. If I actually think of this expression as division instead, I can essentially use the distributive property here. I can divide the x out of the 2x, and I can divide the x out of the 3. Now thinking about it this way, these x's do cancel now, and so that would leave me with a 2 minus a 3 over x. But notice the difference is it's not just -1 that's left over, because it wasn't just a 3, it's a 3 over x. And so now, when x equals 10, this expression turns into 2 minus 3/10, which is indeed 1.7, just like we saw it was a second ago. When x equals 20, this becomes 2 minus 3 over 20, which again is going to be 1.85, just like we saw a moment ago. Or like I said, this can actually equal -1 if we let x equal, what did we say, 1, because this turns into 2 minus 3 over 1, which is indeed -1. But all those values depend on what x are, and this expression gives us back the right values as we change x, whereas this expression up here only gave us back one value, which only worked in one particular scenario. So the bottom line is, we actually can do some form of canceling, not just randomly or haphazardly canceling out a single x on both top and bottom, even though we see the plus or the minus sign, which we know Mr. Ricchuiti said over and over again, don't cancel that way. But if we divide that x out of everything, again, almost like using the distributive property. So let's actually try that on example 1a and 1b, I suppose, in a moment. So for example 1a, we have 3r squared minus 15r divided by 3r. And you'll notice in this lesson, I mostly write the divided by signs as fractions, big fractions. Keeping in mind the principle we showed just a moment ago, I can't just randomly cancel out r's and hope that I end up with the right expression. But I can split this into two different fractions, 3r squared over 3r minus 15r over 3r. And then in each of those individual expressions, I can start canceling. Now, I cannot any longer cancel crossways. So in that sense, no, we still can't cancel across plus or minus signs. That minus sign in the middle there, that is a barrier between these two terms. But within the individual terms, r and r squared leave r. 3 and 3 leave 1, right? We say nothing usually, but we mean 1. R and R leave 1. 3 goes into 15 5 times. And, I always like to do this thing where I highlight what's left over. In this case, I'm also highlighting the minus sign because, again, that didn't go anywhere. This expression is R minus 5. One thing that I hope will give you confidence in this is that this is a problem we could have just approached a few days ago with our factoring. You might notice in the numerator, 3r squared and 15r both have 3r as a factor. If I pull the 3r out, it leaves r, and then if I do that out of the 15r, it leaves 5, and so I get 3r times the quantity, r minus 5. Of course, the original denominator, 3r, didn't go anywhere, and you might notice at this point, oh, well, 3r and 3r cancel out, and what's left? R minus 5. Same thing we got when we tried it this new way, splitting the fraction up, using that monomial denominator to cancel as much as we can, and then obviously having the minus sign left over. One thing I would wonder, looking at example 1a right now, is, I guess that's fine, Mr. Ricchuiti, that we did this new way up here, but why don't we just keep doing the way that was working as of a couple days ago, where we factor and then we cancel out common factors? And the answer is that although this one had a complete common factor that we were able to factor out and then cancel, not all such expressions do. So take a look at example 1b. We have n squared plus 10n plus 12, and the whole thing we want to divide by 5n. Now, we have one big problem here, which is that even if I tried to do this kind of process where I factor out a common factor and then hope it's the same and therefore will cancel with some factor in the denominator, I can't even factor this numerator. There are no two integers that multiply up to 12 and add up to 10. And so even if I wanted, I can't even factor that numerator if I wanted to. And so definitely the factoring and canceling won't help here. It's not going to help us divide these polynomials. But with my new tool, I can say, oh, this splits up into 3 separate fractions, n squared over 5n, 10n over 5n, and 12 over 5n. And then within those individual fractions, so again, this is one individual term. This is another individual term. This is another totally separate individual term. When I say individual terms, I'm thinking to myself, what is separated by the plus sign? Within these individual terms, I can cancel out common factors. N squared and n, leave an n. 5 goes into 10 twice, and my n's cancel. 12 over 5n, actually nothing cancels. And so that's how I end up with my expression here, n over 5 plus 2 plus 12 over 5n. Definitely not the kind of answer we would have gotten a couple days ago, and an answer we can only get, because again, in this case we can't factor, we can only get this answer by doing the actual division. All right, so I'd like you to try this on your own. Take a moment and work out Check Your Progress 1A and 1B. All right, so there you have it. Those are my answers for Check Your Progress 1A and 1B. 1A, we split it up into 2 separate fractions. Those separate fractions we can cancel some common factors out of. A q squared and the 3 come out of the first fraction. A q and a 3 come out of the second fraction. And so it leaves us with the expression q squared minus 2. Check Your Progress 1B, we split it up into 3 fractions. 2 and a t squared cancel out of the first expression. The t squareds alone cancel out of the second fraction. And then the 2 and the 12 have a common factor that cancels in the third expression. I've highlighted what gets left over here, so we have 2t cubed minus 5 over 2 minus 6 over t squared. And notice at this stage, I'm not saying, oh, we should cancel the t squared out of the t cubed, right? Because they are separated by these barriers, the minus signs, and so they stay totally separate. If our denominator is a monomial, that is a very good way to divide it out. Let's say our denominator is not a monomial. Let's say I'm looking at example 2 here, and I have s squared plus 6s plus 7, and I want to divide that by s plus 7. Now, I'm not going to do this the way the book does, because the way the book does it here, we've already done. Factors the numerator. We happen to share a common factor, numerator and denominator, and so we cancel out that common factor. That's fine. You should definitely do that. If it works, it works. That's wonderful, but it's nothing new. I want to show you something new. I want to show you polynomial long division. Polynomial long division looks like this. I mean, let's think about, first of all, something like, say, I guess let's do like 156 divided by 12. Yeah, let's do that. What would we have done back in 4th grade if we had seen this problem, 156 divided by 12? Well, we would have taken this bottom part, which you may remember, you may not, is called the divisor. And we would put it on the outside of the house, right? What house am I talking about? We draw this big sideways L, and we would put that 12, that divisor, on the outside. That's where a divisor goes. And then this part up here is what we call a dividend. And no, not dent, not Harvey Dent, dividend, right? And then the dividend goes on the inside of the house. And then we do this process. We ask ourselves, well, how many times does 12 go into, say, 1? Well, obviously the answer is it doesn't, right? And so then we move over and say, well, how many times does 12 go into 15? So we kind of isolate the numbers as we go. And that we have an answer to, right? 12 goes into 15 one time. And then what do? We say, okay, that's a part of our quotient, but it's not the answer yet. One of those 12s, that one time that it goes in, actually leaves 3 behind. We have to subtract to find what it leaves behind. And then we bring down the 6, and we start the process over, right? How many times does 12 go into 36? 3 times. Exactly? Well, let's find out. 3 times 12 is 36, and we subtract, and this right here is what we call, ooh, I need some more colors. This would be our remainder, right? If the remainder is 0, then yes, it goes in exactly. So in this case, 12 is actually a factor of 156 because it goes into 156 exactly 13 times. And then finally, this part up here is what we call the quotient, right? Well, we can do all these same steps with polynomials. So what would that end up looking like? Well, this part down here is our divisor. This part up here is our dividend, and we're trying to come up with a quotient. So we're going to draw our house, dividend, s squared plus 6s plus 7 goes inside the house. Divisor, s plus 7 goes outside the house. And then we start this process, right? Now, we can't ask the question, how many times does s plus 7 go into s squared plus 6s, or maybe just s squared, or maybe the whole thing at once. We don't really know right now. Because they're polynomials, they're not numbers. They don't go into something some number of times. So we have to ask a different question. I want you to focus on what we call the leading terms, which are just the first terms in each polynomial. And I'm not going to ask how many times does it go in. I'm going to say to myself, what times this s would make an s squared? And the answer to that is what I write up at the top, s, right? S times s is s squared. And just like over here, how we multiplied the 1 and the 12 to find what's left over, we're going to multiply the s and the s plus 7. Notice we didn't multiply 1 times 1, right? We did 1 times the whole number. We're going to do s times s plus 7. This is not a 5, it's an s. S times s is s squared. S times 7 is 7s. And then what did we do after that? We subtracted, right? So we're going to subtract, but we have to subtract the whole polynomial. So I usually remind myself of that by putting these big parentheses here. S squared minus s is nothing. That should always happen. That part should always go to 0. But 6s minus 7s. Be careful with your signs here. I'm not doing 6s plus 7s is 13s. 6s minus 7s is negative 1s. And then I continue the process. Just like I brought the 6 down over here, I'm going to bring down the plus 7. And then I'm going to say, not does, how many times does 12 go into 36, but what times this s would make a negative 1s. And hopefully you can tell, oh, that's a minus 1, right? And then again, I'm going to multiply in, just like I did a second ago with the 13 times, or the 3 rather, times the 12 to get the 36 down here. I'm going to do negative 1 times the s plus 7. So that makes negative 1s minus 7. And then, of course, we're going to... Wait, no, something's gone wrong. Oh, well, what's gone wrong? Why didn't you guys stop me? This is a minus sign. I just wrote the problem down wrong initially. Sorry about that. So that means that this is also a minus sign. Okay. Now, I want to make sure that I subtract. Negative 1s minus negative 1s is 0. That should always happen. Negative 7 minus negative 7. Again, be careful with your signs. Negative 7 minus negative 7 is really negative 7 plus 7, which of course is also 0. And so let's make sure we can still keep track. This down here is our remainder. And because it's 0 here, that means that our quotient is complete, and s plus 7 must have been a factor of the original dividend, right? That's what this part right here is. This was our dividend. Out here, we said this was our divisor. And then finally, up here at the top, we have our quotient. That's what we're actually interested in here. This is the quotient of these two polynomials. Okay, so I'd like you to try this process yourself on Check Your Progress 2a and 2b. You'll notice I am writing both polynomials in descending powers of x. So make sure that you do it that way, not 3 plus b, otherwise it'll get really confusing. I'm actually just going to go ahead and talk through this one because this is a pretty confusing process. So first of all, I asked myself, not how many times does something go in, but what times a b would make a b squared. Those are our leading terms. B times b is b times b is b squared, b times 3 is 3b, and then we would subtract here. B squared minus b squared is 0. That should always happen. Negative 2b minus positive 3b is negative 5b. Always be careful with those signs. Bring down the minus 15, and then keep going. What times b would make negative 5b? Negative 5, right? Negative 5 times b, negative 5b, negative 5 times 3, negative 15. And again, we're going to subtract. In this case, you should be able to tell pretty easily, oh, it's going to make a remainder of 0 again. And so our quotient is simply b minus 5. Check Your Progress 2b. We've got x plus 7 being divided into x squared plus 3x minus 28. What times x makes an x squared? X, right? Okay. X times x is x squared, x times 7 is 7x. We want to subtract. X squared minus x squared is 0. That should always happen. 3x minus 7x is negative 4x. Hopefully that's making sense. Minus 28 we bring down, and we start again, and we say what times the x would make a negative 4x? And the answer is negative 4. Negative 4 times x is negative 4x. Negative 4 times 7 is negative 28. And again, hopefully you can tell relatively easily, leaves behind 0. So x minus 4 is our quotient. In other words, if we were to write out their original expression, x squared plus 3x minus 28 divided by x plus 7, the answer to that would be x minus 4. Now, all three of those examples, the Check Your Progress problems and the example 2, had no remainders. Of course, you might imagine sometimes we do have remainders, right? So again, let's go back to a numeric example first. Let's say I had 162 divided by 12. We would say, well, 12 goes in to 162. How many times? 12 goes into 16 once. 1 times 12 is 12. 4, bring down the 2. 12 goes into 42 3 times. 3 times 12, 36. But this time, something is left behind, right? This one has a, wait, what color did I do remainder in? This one has a remainder of 6. So there were several ways we used to deal with this. When we very first learned how to do long division, we just said R6. So 12 goes into 162 13 times, leaving 6, right? Remainder 6. But very quickly after that, we said, you know what? Let's actually just write this as leaving 6 out of 12. In other words, we created a mixed number with our remainders. And so then we would simplify if we could, and we would say, so the answer is 13.5. We can do the exact same thing with polynomials. Take a look at example 3. And again, I actually want to draw the house to be able to do this. X squared plus 3x minus 24 goes inside the house. X minus 4 goes outside the house. And I start looking at those leading terms. What times x makes x squared? And the answer is x. And then we multiply, right? X times x is x squared. X times negative 4 is minus 4x. And of course, we are looking at, well, what's left over? We subtract. X squared minus x squared is 0. That should always happen. 3x minus negative 4x, be careful with your signs, is positive 7x. And then we bring down the 24, and we start over. And we ask, x times what makes 7x? And the answer is 7. So we put a plus 7 up here. 7 times x is 7x. 7 times negative 4 is not negative 24. Instead, it's negative 28. And so when we subtract these, we don't get left 0. We actually get left positive 4. And if you're not sure why it's a positive 4, you need to practice your integer operations more. But trust me, it is a positive 4. So what do we do with that? Do we write remainder 4? Do we just keep going with the process? Because now it's variables. What times x makes a 4? And you can see, no, that doesn't really make sense. Nothing times x makes a 4, at least nothing that we would naturally think of. But no, let's make a mixed number, right? Up here, we put that remainder 6 on top of 12, right? That's where we got 6 over 12 from. Here, we're going to put that remainder 4 on top of x minus 4. And so that gives us what we call a mixed expression. This is our quotient right now, including the fractional part. X plus 7 plus the rational expression 4 over x minus 4. And that is polynomial long division with remainders. Take a moment and see if you can work out for yourself. Check your progress 3A and 3B. Okay, don't love this example because you're going to get confused, so I'm popping in here. Pop! What times y makes a y squared? Y, right? But then when we distribute here, we get y squared plus 3y. And when we subtract, we already get 0. So by the time we bring down the positive 12, all that's left over is 12, right? 0 plus 12 is 12. And nothing times y is going to make 12. So this is already our remainder. 12 is already our remainder. And so if we were going to do the same thing we did before, we would put 12 on y plus 3. And so that is the quotient here. This equals y plus 12 over y plus 3. So not a great example to start with because it kind of got confusing where we were missing something. But the process is the same. Okay, so go on with check your progress 3B. I don't think it's going to happen again. All right, there's your answer for check your progress 3b. We have 3x minus 6 plus 15 over x plus 5. We've got one more example to work out, but let me make sure my boys are not crazy. All right, just one more problem to get done. Let's take a look at example 4 and the associated check your progress problems. Not a new process, just a little wrinkle. So we have a to the third power here, a cubic polynomial. Cubic polynomials have been in the news lately. You guys should Google why. And we are dividing it by a minus 2. And of course, we're going to set up our house. And we're going to put the a minus 2, our divisor, on the outside. And the a cubed plus 8a minus 24 on the inside. And then we ask the same question we've been doing. What times a would make an a to the third? And you'll notice this time, since we're dividing a cubic polynomial by a linear one, or a third degree by a first degree, it's actually a to the second that ends up being our partial quotient. We would then multiply that back in, and we would get a to the third minus 2a squared. But then you'll notice a problem. 8a cannot be subtracted by 2a squared. They're not like terms. So what we have to do is make sure that we have what's called a placeholder. You'll notice our original polynomial was cubic, but it was not just cubic, it was also missing the a squared term. And so we have to supply a 0a squared, right? There were no a squareds, and so 0a squared is the same thing. So now, when we have that minus 2a squared, we have something we can actually subtract it from. And so we can go ahead and subtract a to the third minus a to the third is 0. That should always happen. Those should always match. But then 0a squared minus negative 2a squared is positive 2a squared. And of course, we can bring down the plus 8a and then just continue the process from there. What times a would make 2a squared? And the answer is 2a, right? So I'm going to put a plus 2a up here. 2a times a is 2a squared. Those should always match. 2a times negative 2 is negative 4a. And then we want to subtract, and we should get positive 12a. And we can bring down the minus 24. And then we need a plus 12. 12 times a is 12a. And in this particular case, it just so happens that we end up with a remainder of 0 at the end of that process. And so a squared plus 2a plus 12 is the quotient, and it turns out a minus 2 divides into a to the third plus 8a minus 24 evenly. So using your placeholders, go ahead and work out check your progress for a and for b. So we're just always making sure that our powers count down. That's what I'm doing here. 4, 3, 2, which was missing, 1, and then of course nothing. I don't know why they do these things. They choose the worst examples. So obviously, with all these zeros, that would just be another plus 0 up here, and we would just need to bring down the 6c, and then finally that would be plus 6. And to get 6c plus 12, I guess we should also bring down the minus 10. And so we end up with negative 22. So a remainder of negative 22, meaning our quotient is c to the third plus 6 minus 22 over c plus 2. Very annoying, but there you go. That's that. Maybe check your progress 4b will be a little better. As far as I can tell, this one doesn't even need a placeholder.
The kitchen isn't closed, Dad.
Thanks, buddy. All right, and there's check your progress 4b. 3x squared minus 7x plus 5 minus 11 over 2x plus 10. So that is polynomial long division. That's what we call polynomial long division. We can actually divide polynomials by using something like our numeric long division process. Of course, if our denominators are monomials, you'll remember way back 30 minutes ago or so, then it's a lot easier to just split up our fractions and cancel individually. When the denominators are not monomials, however, you will want to do that process I just outlined with the polynomial long division. Good luck on the homework. Comment with any questions that you have. Make sure to like and subscribe below, and I will see you guys on the next one.